Alright, today we're going to talk about cross-sectional volume. And what we're really going to talk about here is when you have an irregular shape and you want to find the volume of that crazy looking shape, you can do it by looking at cross-sections. So one of my favorite examples is always thinking about an egg slice. So if I take an egg slice right here, and I want to know the volume of the egg, if I want to know the volume of this egg, I can figure out what the volume of each one of these individual cross sections are. And if I slice up an egg, I'd have a whole bunch of cross sections that are circular discs. Add up the volume of all the discs, I get the volume of the egg. Same idea over here if I look at a slice of bread. If I want to look at bread, each individual slice added up would give me the volume of the whole. Now, when I cut up this egg down here, the egg has cross sections that are circles, whereas this baguette almost has cross sections that look like semicircles. I know they're not exactly semicircles, but work with me here. So I would have kind of these semicircular discs, and those make up the bread. If I have a loaf of sandwich bread, I have cross sections that are basically, these things would be like squares. If I look down here, this is just like a mathy interpretation of one, not a great realistic version, but this, if I sliced it, would give me cross sections that are triangular prisms, just like that. And if I took a pear, even though the bottom of the pear is kind of oblong, each subsection of pear would again be these semicircular discs. So that's what we're going to be talking about today. How do I end up with these cross sections and what do I do with them? So if we come over here, if I want to use integrals to find the volume, if I have a known cross-sectional solid, the volume of a solid of a known cross-section has something to do with the area of each cross-section, and here's why. So if I think about that pear from the last time, and I look at that pear's cross-section, if I look at a semicircular cross-section, the volume of that kind of semicircular disc of pear, the volume of this piece would be the area of the face times the depth. So if I took the area of whatever face I have times the depth and then added all of those together, I'd get the total volume. Same thing would work for the sandwich bread. If I considered each piece of bread kind of a square, I know that's a terrible drawing, each kind of piece of bread is kind of a square, the area of the face times the depth would give me the volume. Now, area of the face, A of x, dx, that's going to be your depth and make your volume, and that'll make more sense in a minute when we get down to an example. So far so good, and then the integral represents the fact that we are summing everything, that we're taking the sum of a whole bunch of pieces. So if I want to find the volume using this method, what we do is we figure out what each cross-section looks like, we find an area of each cross-section, and then we find our limits of integration and integrate. So let's come down here. Find the volume of a solid created whose base is the region enclosed by x and x squared, and cross sections are squares. So let me quick sketch that. So here's y equals x, and right here we have y equals x squared. And if I look at the region right here, that's what I'm talking about. So if I want to find the region in between and I want to make cross-sectional solids, here's what basically happens. We measure the distance between each of those with a representative rectangle. Then that rectangle, kind of like a chia pet, grows up and out of the page and makes a square. Then I measure this distance, grow up and out of the page, make another square. Down here my squares are getting consecutively smaller, and I have a whole bunch of squares. Now that's a little bizarre looking, so that's why I've drawn it again over here. Basically, here's the curve y equals x squared, and back here I have the curve y equals x. Measure the distance, grow up and out of the page, and we have a square. Here's the distance up and out of the page, we have a square. Now, each of those square discs looks like this. So there's my square disk. Now, since I'm dealing with representative rectangles, oh, I didn't mean to erase that whole thing. Hold on a second. And since I'm dealing with representative rectangles, each of these representative rectangles basically kind of turns. So this right here turns and becomes the base of each square. Well, the distance right here for the base would just be the height of this rectangle, and the height of that rectangle would just be x minus x squared. Since this is a square, the height would also be x minus x squared, and this depth back here would be dx, because that depth is really this distance, which is a small distance with respect to x. The volume of this square is just going to be length times width times height, or length times width times depth in our case. And since I'm going to add a bunch of those up, I'm really taking the integral on the region shown, which in this case would be 0 to 1. So I have the integral of x minus x squared squared from 0 to 1. Now, how does this have to do with the formula that we had up top, a of x dx? Well, if I kind of start from scratch down here, I would say, all right, it says that volume is the integral of a of x dx from a to b. Well, in this case, a and b are 0 and 1. A of x represents the area of a square. The area of a square is side squared. Dx represents our depth. So the area of the square times the depth gives me volume. Side squared times the depth. Well, these are supposed to be the same variable. So now I need the side of a square in terms of x. That's this thing right here. The side of the square is the distance between the two functions. So that's how I end up with the integral from 0 to 1 of x minus x squared dx. And now I'm just going to put that into the calculator. So I'm going to bring my calculator up. I'm going to go math 9. Come on. There we go. And I'm going to take the integral from 0 to 1 of x minus x squared. Oops, I forgot to hit the squared button. Squared. There we go. Dx. Type it into my calculator. I have 0.03 repeating. And that is the volume of the weird solid I would get when I connect all of these boxes together. All right, moving on, we're just going to do a couple examples and then kind of wrap it up at the end. I think the more examples we do, the easier it's going to get. So find the volume of the solid whose base is S and whose cross sections taken perpendicular to the x-axis are semicircles. I'm going to quick go back to that pair because that's kind of what this is. If I look at just this part of the pair, that's kind of what we're dealing with right now. We have kind of like a pointy end, and each slice is going to be a semicircle. So keep that in mind as we look at this next example. So find the volume of the solid whose base is S and whose cross sections perpendicular to the x-axis are semicircles. All right, so I'm going to start with the formula, the integral from a to b of a of x dx. A of x is the area of the cross section. The cross section is a semicircle. So I need the integral of pi over 2 r squared dx. Pi over 2 because it's a semicircle. It's not a whole circle, so it's not just pi r squared. Pi over 2 r squared is the area of the semicircle. A and b would be my boundaries here, so that would be 0. This would be a. We'll call it a. So 0 to a, and I'll deal with that in a minute. Pi over 2 r squared dx. All right, now I need r in terms of x. So I'm going to draw in my representative rectangle, and then I'm going to bring it down here. So that rectangle kind of turned, and it's making these semicircles. Well, the radius of the semicircle is half the distance between the two curves. So my entire distance between the two curves would be 2 minus x cubed minus tan x. Sorry, I don't know what that blue line was. 2 minus x cubed minus tan x would be the whole thing. So my radius would be half of that. Pi over 2, 2 minus x squared minus tan x, all over 2. That's what gets me my radius. Pi over 2 r squared dx. Now I just have to put this into the calculator. So I'm going to come back over here, and y equals, I'm going to make sure I'm in radians here. Yep, I'm in radians. So I'm going to come to y equals, and I'm going to put in y1, I'm going to put 2 minus x cubed. And in y2, I'm going to put tan x. I'm going to graph it and find where they cross. This is a very pretty graphing calculator on here. 2 minus x cubed. Come on, tan x, you can do it. Alright, so they intersect right about there. I just need to figure out what that is. So I'm going to do second, calc, number 5, first curve, second curve. I'm guessing right near there anyway. There's my intersection. I'm going to store that as A. So now I have A. Now I can finally type in this integral over here. So math 9 from 0 to A. And then I have pi over 2 times, let's see, I'm going to use my vars. Vars y vars function y1 minus vars y vars function y2, because I'm taking the difference of those two functions, cutting that difference in half to make a radius. Notice there's 2 divided by 2's. Dividing by 2 because it's a semicircle here, dividing by 2 to get the radius instead of the diameter over here. Let's see, everything's in there. dx, hit enter, and I get 0 because I forgot to hit y2. Silly Mrs. Vibber, so let me pull that back up. Sorry about that, I meant to hit y2, I thought I did. Vars, y vars, function y2. There we go. And my final answer, 0.911. That is the volume of basically the tip of the pear. All right, moving ahead. Find the volume of the solid whose base is the region R, okay, so dealing with R now, and whose cross-sections taken perpendicular to the y-axis are rectangles whose height is twice their width. So if I'm dealing with the y-axis now, I need to draw my representative rectangles with respect to the y-axis. So now I have this, and I have rectangles whose height is twice their width. So the width down here is the difference between the two curves with respect to y. So I'm going to have a dy this time. So to find my volume, I need to take the integral from a to b of a of x dx. But in this case, we're dealing with y's. So I'm going to take the integral from 0 to whatever this value is. Now, since we already did example 2, I'm going to call this value right here tan a. Because once I knew a, which was right here, tan a would be the y value. So I'm going to take the integral from 0 to tan a of my area of a rectangle. Well, the area of a rectangle is length times width, and I know I need dy. All right, so length times width. My width here would be the difference between the two curves in terms of y. So let's see, the outermost curve would be this cubic right here. But when I make that an x equals, it's going to turn into x equals, let's see, 2 minus y cube rooted. So my outer curve is going to be the cube root of 2 minus y, and my inner curve is going to be inverse tan y. All right, so that's my width. My length would just be twice that because I want rectangles whose height is twice their width. So this is going to become the integral from 0 to tan a of length times width. So the cube root of 2 minus y minus inverse tan y times twice this amount. And just to save space, if I'm doing this thing times 2 times this thing, wouldn't it really just turn into 2 and then this would be squared? I think it would. So then we'd have a dy. I'm going to go back to my calculator and evaluate it. So I'm going to do math 9, the integral from 0 to tan a, and then come into my integrand, and my integrand is going to be 2 times the integral of the cube root, let's see, I'm just going to do that with exponents, the cube root of 2 minus x to the 1/3 minus inverse tan x, and that parenthesis, let's see, that ends that, and this parenthesis, come on, square it, and dx, and that should be the right integral. 2 times 2 minus x to the 1/3 minus inverse tan, all squared, 1.175. And that is the volume. And last but not least here, find the volume of the solid whose base is the region enclosed by y equals sine x. I should draw that. And y equals x squared minus pi x. X squared minus pi x, that's kind of weird. I just did that to give myself this region right here. So I'm taking this region right here, and I'm going to take that region and grow equilateral triangles up out of it. So what's going to happen is I'm going to take a representative rectangle that looks like this, and from it I'm going to grow triangles, and it's going to look like this thing right here. But long story short, let's let the formula speak for itself. I'm going to take the integral from a to b of a of x squared, a of x dx, not squared, a of x dx. Equilateral triangles. All right, so let's deal with an equilateral triangle for a second. Equilateral triangles look like this. And if I want the area of an equilateral triangle, let's see, you know what I'm going to do? I'm going to go back to A2 trig and say, you know what, if this is an equilateral triangle, this is a side, this is the same side, and that's 60 degrees. Remember that formula where the area of a triangle is 1/2 AB sine C? Let's go with that. So this is going to be the integral for ours from 0 to where those intersect, which is pi, of 1/2 AB sine C, there's the area, dx. So in our case, that's going to be the integral from 0 to pi of 1/2 AB side squared sine C, so sine 60. I know we're in calculus. You know what? We should not do 60. Mrs. Vibber, don't write 60. We should write pi over 3 dx. All right, so this is in terms of x, and that's still an s. All right, so my side in terms of x would just be the length of this rectangle, and the length of that rectangle would just be top curve minus bottom curve. So this is going to turn into the integral from 0 to pi of 1/2 sine x minus x squared minus pi x squared. And then, pardon me, x squared minus pi x, and that, square it, times the sine of 60, which you all know is root 3 over 2, times dx. One last one to put in our calculator, and we are good to go. So I'm going to have math 9, the integral from 0 to pi of 1/2 times sine x minus, let's see, sine x minus x squared minus pi x. So I have that, sine x minus that thing. I'm going to end the other parenthesis from right before the sine x, so now I can square it. Let's see. Oh, I need my times root 3 over 2. So I'll stick that at the end in here. So times root 3 divided by 2. There we go. Oh, forgot a parenthesis there. And dx. Please give me a nice number that works for me. 8.56 something. 8.56 what? 8.561. And that is the volume. All right, so what did we just do? Long story short, first you figure out the integral from a to b of a of x dx. Then you decide, all right, what's my cross section? Is my cross section a square? Then it's going to be a of b of s squared dx. Is my cross section a triangle? Then it's going to be a to b of, what was that? 1/2 ab sine c times dx. Is my cross section a semicircle? Then it's going to be the integral from a to b of pi over 2 r squared dx. Once you get one of these setups, then you need to turn these inner portions into something in terms of x. Usually what that means is that this inner portion here is going to be one function minus another function, because the length of those representative rectangles always have to do with one function minus another. Once you get everything in terms of your functions in terms of x, a and b just have to do with your endpoints. Throw it into your calculator, and you are good to go. We will talk more about this when you see me in class, but there is your example of how to do cross-sectional volume.